here is the example of K nearest neighbor classifier before we can shift to the practical part of it. So a company conducted a questionnaire where they asked people about their opinion regarding the paper that they are producing and classifying the paper into good paper or bad paper based on two factors. The first factor is the acid durability. How long does it take for the paper to dissolve in any given specific acid? And the second one is strength. How much kilogram per square meter can the paper carry? So what they did was they asked people to judge their paper based on these two criteria, and what scores were given from 1 to 10. Some amount of scores were given. So this is what we have over here is the training data, where some values for x1 are given, some values for x2 are given, and then the y classification or final result is given. In this particular case, we've got 4 examples as the training data, 2 of which are bad and 2 of which are good. So the next thing is that the company produces another paper and wants to find out if this is a good one or a bad one. And in the laboratory tests that they conducted, they've got x1 equals to 3 and x2 equals to 7. Now instead of having to go door to door again in order to find out how good or bad their paper is, what they want to do is find this in the result of or the label of this paper using classification. The first thing that we need to do in order to use the K nearest neighbor for the given problem is decide the number of nearest neighbors or decide the value of K. In this case, we've set K equals to 3. Since we have 2 classes, so it is a safe bet to use K equals to 3. The other thing, the second step is calculate the distance between the query instance and all of the training samples. Now please remember, K nearest neighbor is called the instance-based learning because of this, because at any given runtime, it keeps or it stores all of its actual or training data members in the memory and then calculates the new or test sample based on that or based on distance from the actual members. So the next thing that we do is we take the value or the test value 3 and 7 and we find the distance of 3 and 7 with each one of these. So there is 7 minus 3 and 7 minus 7, and then we calculate the distance from the first example or first sample, calculate the distance from the second sample, and so on and so forth. So for each value of x1, we calculate the difference between the x1 of the training sample and x1 of the test sample. Similarly, x2 of the training sample and x2 of the test sample. And we keep doing that for all of the examples in the training sample. Then we end up with the distances of the current or test sample with all of the training samples. The third thing that we do is we sort these distances in order to find which are the nearest neighbors. The whole idea is to find which are your closest or nearest neighbors. So the third thing that we do is we sort the distances, and based on these distances we classify which neighbors are near. For example, this one, and this one, and which neighbors can be discarded. Once we're done with that, the next thing that we check is the labels of these nearest neighbors. And according to our classification or our arrangement or organization, what we see is 2 of these are good and 1 of this is bad. So taking the majority rule, we'd say that the new example is closer to the good samples. So it is now classified as a good paper, or it is put in the good category. So wrapping up the topic today, some of the important things to consider in K nearest neighbor are, the first one, the value of K. The value of K changes or determines the decision boundary. So if we have too small a value of K, we have an overfit or we have very close and complex decision boundaries. And if we have too loose or too large a value of k, then we are going for underfit or an extremely unnecessarily generalized problem. So it would again not give you the correct solution. The second thing we did was the value of k should be odd, and we usually keep it odd in order to get the majority voting. In even numbers, it is possible that all classes have similar number of items that they are contributing. So in order to get the majority voting, it is better to keep the value of k as odd. The second thing that we determine is the distance metric to be used, because we saw that different distance metrics give us different areas, and different areas mean that different points are considered. So some points that lie in this circle may not be considered equals to those points that lie inside the rhombus. So the next thing, KNN, is pretty simple to implement, but this simplicity comes at the cost of resource. Since all of the training examples are placed inside the memory at any given time, so it is not very resource efficient. KNN can be applied for datasets that have smaller number of values, but not for datasets that have too huge values or too complex or too many dimensions to their features. It is non-parametric. We do not look at any properties or statistical properties from the population, and it is instance based, as we just said that all of the instances are placed in memory at any given time. So this wraps up our discussion on KNN. We'll be doing ANN in the next lectures, and hope to see you there then.